Saxon Advanced Algebra, Lesson 88 continued. We finished 88.1, now we're on 88.2. I'm going to rewrite my formula. Don't look, I'll cover up what I'm writing, but you try to write the formula without looking at it. Try and see how much you remember already. Okay, compare to me. All right, two-part problem, solve for K first, apply what you know to the second scenario. The number of bacteria present when the experiment began, okay, that makes it easier to understand. The original amount was 1,200. After 100 hours, there were 2,700 bacteria present. Assume exponential growth, that means we can use this, and find the time required for the number of bacteria to increase to 30,000. So we want to know at what time will the amount be 30,000. So we want to solve for T. And then it says sketch the curve, which we know is super easy. Okay, so what I like to do is draw a line between where I've been given information I can use and then where I have a question. So now let's do step one. All right, the A to 100 is 2,700 equals the original amount, 1,200, times E, K, and then my time in the second amount is 100. 100 what? I don't even remember. 100 hours. It doesn't matter if it's hours, days, weeks. Assuming John gives us matching time frames, we can just put it up there. We don't have to worry about the units. All right, the first step is always to divide away this constant number. And this simplifies to 2.25, right? Yes. I'm not even going to show that calculation. It is nice. I mean, you can just do this, right? 27, 12, it goes in there twice. That's 24. Bring down a 3, put in the decimal. 2 more times, 24. And there's the 5, right? When you're using your calculator for more advanced calculations, it becomes a real temptation to just use the calculator for everything. Please fight that. Please try to challenge yourself by doing some of the easier calculations by hand so that you don't fall into that trap of being dependent on your calculator for everything. It really does change your brain's ability to think when you just rely on the calculator. So we're at the point now where we have to use it for some things, but we don't have to use it for everything. So resist the temptation to just do the easy calculations. Okay, 2.25 equals E to the K times 100. I could reverse those. I wish I would have, but I didn't. It's okay. Now we know that we want to solve for that, so we have to get it out of the exponent, so we're going to take the natural log of both sides. I'm going to use the power rule version of the laws of logarithms to jump that down. And it's 100K. I made a mess of it. Okay, this we remember is equal to 1, just like the common log of 10 is equal to 1. So we can drop it out of our calculation. This we find a calculator value for, and it is 0.813093. Equals 100K, and then we divide away the 100, and we get K equals, and John goes all the way out to 5 decimal places. How do you know how many decimal places to use? I think 4 is a good place for you to challenge yourself. 5 is a bit much. So if you want to round this to 4, I'm fine with that. I'm going to continue to work it with 5 just to show you that it doesn't hurt. But I would say 4 decimal places is plenty for you. Okay, so that's our value for K. Yay. Now we're ready for our step 2. We want to find out what the time would be that we'd have 3,000. So our amount at that time, we plug that in, right? That goes here, equals the original amount times e to the k times t, and we don't know what t is. So that's the variable we're solving for, right? This is not a variable, that represents a number. Okay, we have our work cut out for us. We divide both sides by 1,200. Again, you can do this as a side calculation. I'll tell you right now, it works out to 25. I work these problems before I start this lesson so that I'm sure everything works and I am not perpetuating any mistakes. Whenever I make a video, I always work the problems out ahead of time so that I know what I'm talking about, kind of. Okay, 25 equals e to the 0.00811 times t. Now we have to take the log of both sides again, just like we did up here. We have to get this, anytime you have a variable in the exponent, you take the log to get it down. So it will be the natural log of 25. We know that when we take the natural log, we'll get this situation again, and this will go in the front of it, so we know it'll be equal to 0.00811 t. All right, so I'm not showing this step, but that's what's happening here again. I hope that doesn't confuse you. Okay. Now we divide, we get a calculator value for that, and it is, oh, I'm looking at the wrong place, 3.219. 3.219 equals this 0.0081 t. We'll drop off that 5th decimal place. Well, let's just leave it. I don't want to change horses in the middle of the stream. And then you can use your calculator to divide, and we get t equals 396.92. So that's the number of hours it will take us until the amount of bacteria in this particular experiment reaches the level of 30,000. All right? And so again, our graph can be quite simple. This is time. This is the amount at a given time. And we started at 1,200 and we're going up. That's all you need to show. Okay, so this whole thing is the answer. And that's what John was hoping for. Okay, he puts a 0 here. I guess that's a good idea too. All right, one more. How are you feeling about these so far? I hope what you're finding is that there's a lot going on, but you can manage this. It's not too hard, it's not too scary. Example 88.3. I believe this is our last one. Let me check. No, there's one more. The amount of substance originally present was 400 grams. And after 90 hours, only 380 grams remained. Ah, this is decreasing over time. So we have a decay problem here. That's what we can deduce right away. That's okay, it doesn't make it harder. It's just good to know that at the beginning. Assume an exponential decrease, oh okay, John told us, and determine the half-life of the substance. What is a half-life? The half-life is the amount of time required for the initial amount to fall to 1/2 of the original level. Okay? So half-life means the time to reach the original amount divided by 2. Okay? So we'll set this equal to the time, the amount at that time, and then we have to solve for the t. Okay? So a half-life means the time that is required to reach half of the original amount. Okay, so the first thing we have to do is solve for k, just like always. So we know that, there's where we divide the first step from the second step. 380 equals 400 times E 90K. This time I'm just going to rearrange them. Right, here's our formula. And for some reason, it's always written with the K first, but I much prefer to flip it around when I know the time, but I don't know the constant. I don't like to have letters before numbers. I like numbers first. Okay, that's good. We're good. We're now going to divide by 400. We always do that first to get the whole numbers out of control. This simplifies down to 0.95 equals e to the 90k. We will take the natural log of both sides. So the natural log of 0.95 equals, I'll show the step this time. I feel bad I didn't last time. Right? The exponent jumps down in front. This equals 1, we cross it off. This equals 90k. We use our calculator to find this. The natural log of 0.95 is negative 0.051 equals 90k, and then we divide by 90. And we find out that k equals negative 0. Okay, ready? Here come a bunch of zeros, 3 zeros. Okay? This is how we know we have a decay also, is that our constant is a negative. That's going to make our numbers get smaller, right? That negative exponent means take the reciprocal. It flips things into fraction form, so we know that any amount that has a negative reciprocal is actually going to get smaller as we multiply an increasing time by this. So that makes sense. That's what we would expect to see in a decay problem, is a negative value for k. That is right. Okay, now we're ready to start our second one. Ready? So now, we know that the amount that we want to have at time t is half of the original amount. The original amount is 400, so the amount that we want to have is 400 divided by 2 equals 200. That is the half-life. We know that's the amount that we want. We just don't know how long it's going to take. So we substitute it in. 200 is the amount we want, and that's equal to the original amount times e raised to the power of k, which is negative 0.00057 times t. T is the amount of time we're trying to solve for. So we do the same thing we've been doing. We get rid of the whole numbers. The whole number coefficient here is what we want to get rid of first. 0.5 equals e to the t, not k, sorry, my bad. Our variable is in an exponent, so we take the log of both sides. The log of e will cancel. This is what we'll have left. It will have jumped down, right, just like we did here. This jumps down and goes in front. So this jumps down and goes in front. I'll just show you. We take the natural log of both sides. And then I use my power rule to take that down. So, right, there's the log of E. That's equal to 1. It goes away. I find the calculator value for this. It is negative 0.693 equals this. We divide by this monstrosity. And what we get, that isolates the K, right? Because that cancels. We get that K, or I'm sorry, it's a T. I keep writing a K. This is supposed to be a T, right? We know K, the constant is that number. This is the T. T equals, and it's this divided by this. Yes, you may use a calculator for that. What is the number? 1,215.79, and we're dealing in hours per the problem. That's how long it will take us to get, that's how many hours it will take before the original amount of 400 has fallen to its half-life, which means that half of it is gone, so we're down to 200. And now a quick graph, I'll just squeeze it in up here. Here's the time, here's the amount, this is 0, and we're starting at 400, and we're going down. That's enough of a graph to make John happy. This, to me, is the more interesting calculation. All right, one more. So we saw that decay works exactly the same. You just have a negative value for K, and that shows you how it decreases. Example 88.4. Write it one more time. A radioactive substance decays exponentially. Okay, we know that, and that tells us it's a decay problem, so we're going to expect to see a negative K value. After 100 years, 500 grams are left. Okay, so at A to the 100, 500 grams are left. And after 200 years, only 300 grams remain. Find the amount of the substance that was initially present. Whoa, so we have to find A to the 0 and then find its half-life. This problem's different. We've never had a problem before where we weren't given the original amount. So what we have to do is we have to use these two equations as a system to solve for the original amount. Well, first for the constant and then for the original amount. Whoa, that's trippy, isn't it? Okay, so what we're gonna do is we're gonna take these values and write them out as our full equation, and then we'll compare them. Okay, so for the first amount, we'd see that 500 equals A to the 0, we don't know what it is, E times, and it was after 100 years, so it would be 100 times K. Make sense? We're taking this value after 100 years and we're plugging it in here. Now we're gonna do the same thing with the 300. The amount at this point is 300, and that's equal to the original amount that we don't know raised to the power of 200. Okay. Okay. Now, this is weird because we've never quite done this before. This is a system. This is the same system. Oh, this isn't really, I mean, you don't have to think of that as a system. This is definitely a system, though. We have added, we called it elimination. We have subtracted, but what we've never done before is divided two equations in a system. That's what we're doing. That seems weird, but we can do it. We're dividing. 500 divided by 300. Oh, wait a minute. John does it the other way. Yeah. Let's do it that way. I don't want the 500 on top. I want the 300 on top. You'll see why in a minute. I reversed that order for no reason. It just happened that way. Okay, so these equations are exactly the same. I just flipped the order. I put the 300 on top. All right, that gives us 300 divided by 500 is 0.6. Right? That makes sense because if we double this, then it's 1,000. It would be 600 over 1,000. That's 0.6. These cancel. Right? Original amount divided by original amount, that's 1. And we can use our rules for exponents to combine these. If I have 200k minus 100k, then that gives me a final value of 100k. I subtract, right? That is how I get this value. That is why I want the 200 on the top, is because I want this combined simplified value to be a positive number, right? If I'd done it the other way, it would have been 100 minus 200. I would have had a negative exponent. It would have worked out. It just would have been more drama. So this provides a nice, clean, positive exponent. So that's how you could decide is you want your bigger number in the exponent to be on top. I hope that makes sense. All right, now we'll take the log of both sides, and we find out that the natural log of 0.6, the natural log is going to cancel the e, and then this is going to jump down in front, so it will be 100k. And then we'll take the natural log divided by 100, and we'll find that k is equal to negative 0.005. There's the negative k that we expected to see because this is a decay problem. We're good. Now, we can substitute this value back into one of our original equations and find a to the 0, the original amount, right? Let's take this first one. So a to the 100, here it is with the full equation. 500 equals 100 times e times k times the time 100. Beautiful. Wait, no, I did this wrong. We don't know. This is the number of years. We still don't know that. I knew that didn't look right. Okay, so now we can simplify all of this though. So we have 500 equals a to the 0, and then with our calculators we can take 100, multiply it by this, which is just going to be 1, 2, right? So it'll be 0.05. Raise e to that power, and the number that we get e to the minus 0.0. And then what we want to do is isolate this. This is where I'm... Okay, so here's the way John solved this at this point. He divided both sides by e to the minus 0.5. I would simplify it right there. What John does is he flips this up, right? Because this is a negative exponent, so he takes the reciprocal and he changes it into 500 times e to the positive 0.5 equals a to the 0, which works. It just seems kind of unnecessary to add that extra step. So I think it would have been fine to simplify here. But John goes ahead and flips it so that you're simplifying here. It works. In either case, you should get an original amount of 824.36. And if you look back at the problem, you'll see they're measuring in grams. All right? And then, so that's our original amount. And now we still have to find the half-life. So the way that we do that is to say, we want to find the amount of time for half the original amount, which we're just going to call 824. Well, we'll use the... I wanted to round it, but I guess not. Equals the original amount raised to the constant times k. Okay? If we divide both sides by the 824.36, oh, the math is going to get so much easier really fast. Right? Because that all goes away, that all goes away. I'm going to copy to the next page. It's going to be 1/2 equals e to that. One half equals e to the minus, yes, that is our value for k. 2 zeros and a 5 to the minus, and then t. We need to take the natural log of both sides. I'm going to change that to a 0.5. That's easier to work in the calculator. Equals, we take this down, we jump it in front. Natural log of e goes to 1. Right? This value, well, again, John does this clever thing where he says, before we find it, let's just get all the numbers organized. So that cancels. T equals, we find the natural log of 0.5 and we divide it by that, and we will get 138.63 years. John did not ask for a sketch this time, but we would just draw a declining, a decay function that was going down. All right. These problems are very sophisticated. They involve a lot of itty-bitty little numbers in those constants, and that can be challenging, but I hope you see that you have all the tools you need to manage these problems. And the graphing of the exponents, which I know for some of you has been a real bugaboo, that's not a part of this at all. All right, lesson 88. We will talk about this at the video chat. I hope you get a chance to look at it so that we can discuss it. But if not, we'll discuss it next week. Just remind me to ask you about this, how it's feeling in your brain. Good stuff. Thank you, students. Goodbye.